So we talked in the last video about what a function is, and specifically a lot about their domains and ranges and on what intervals they are defined. Here, let's talk about the connection between a function's rule and viewing the graph of that function, which is the set of all ordered pairs that satisfy the function plotted in a coordinate grid. So those graph viewing skills that are important are these four. We need to first recognize that the graph is reasonable. So is the graph that we have either on our calculator, on Desmos, that we've drawn, we see in a book, is that reasonable for what the function's equation is? Two, we want to be able to see all the important characteristics of the graph. Does this graph have an asymptote? Does it have maximums and minimums? How many times does it cross an X or a Y axis? We need to interpret those characteristics. So where are those characteristics coming from? Why does it have a vertical asymptote? Is there something in the equation that can tell me this? And finally, we need to be able to recognize grapher failure. So if we believe that a function's equation should have a reasonable graph, but then we look on our graphing calculator and see something that doesn't seem exactly right, maybe we either have something wrong with our grapher or we've typed something incorrectly to be graphed. So we need to be able to recognize when something like that happens. So here's an example. We want to use a grapher to identify the domain and range, and then draw a graph of this should say function, not unction. So if you don't have a TI-84 on hand, I would suggest going to the website desmos.com. That is an awesome graphing calculator. It's free to use. In fact, in many cases, it is more powerful than a TI-84 or 89. So we want to graph these functions and talk about maybe some of their domains and ranges, interesting characteristics. So let's see, y equals 4 minus x squared. Before I get into its graph, I'm going to try to see, let's see, it's a square root. So the domain's probably not all numbers because I know that square roots of negatives are imaginary. I know that when I plug in a 2 there, I end up with a 0 under the radical. That might be interesting, but the same thing with -2 as well. I bet that has something to do with the domain. Over here on part B, y equals x to the 2/3, that's not one that maybe we're very familiar with. So I think I'm going to leave it to the grapher to talk about that one. Here is the graph of A. Y equals the square root of 4 minus x. Turns out that we have a semicircle. Well, that's kind of neat. And if I look back at the equation, that sort of kind of makes sense, because if you squared both sides of this, you'd end up with a y squared equals 4 minus x squared. And then if you added x squared to both sides, you'd have what? X squared plus y squared equals 4. Hey, isn't that the equation of a circle? So it kind of follows then that this might be half of the circle, and the other half would probably be if we stuck a negative sign in front of there as well. The domain of this function is closed. It goes from -2 to 2, and that makes sense. I'm going to change colors. That makes sense because 2 or -2 here, all the way over to +2 there. Seems like for every one of those x values, we have a point, right? We've got a point that we can graph. The range is also closed from 0 to 2, and I believe that makes sense as well, because if we look on the y value, remember the y's are the range, we start at 0 being defined, and we go all the way up to the number 2 on the y-axis. Next, we have B. This is the graph of y equals x to the 2/3. Kind of looks like a bird with wings there maybe, or an open book. I can see that as well. Its domain is open on its endpoints, and it goes -infinity to infinity, and that is because this graph continues on forever. And we know that because we can plug in just about any value we can imagine into x to the 2/3 and get an output. The range is closed on its left side. It starts at 0, but then it goes on forever towards positive infinity on the y-axis as well. So close 0 to open infinity. All right. Even and odd functions. Here's something that doesn't come up a lot in algebra, but it's a nice thing to know because it's a good way we can describe functions. An even function is an even function if f of negative x is equal to f of x. In other words, if you plug in negative x and simplify, you have the original function. How about that? For an odd function, if you plug in negative x, you end up with the opposite of the original function. Opposite of the original function. And on the next couple of pages, we're going to find out a little bit more. Here we see a little more about even functions. First of all, the graph of an even function is symmetric about this should say y-axis. They are symmetric about the y-axis. Even functions, again, these are the ones where if we plug in negative x, we end up with the original function. So that means a point lies on this graph if and only if the point negative x comma y lies on the graph. And you can see this in a pretty common even function down below. It's y equals x squared. You can see that if there exists a point on this graph xy, there is a point on the other side symmetric of the y-axis, negative x comma y. So another thing to note here, said below, note that the power of x is even. Y equals x squared. The power on that monomial x is even. 2 is an even number. For odd functions, the graph of an odd function is symmetric about the origin. Origin symmetry is another way of saying 180-degree rotational symmetry. Remember, odd functions are the graphs where if we plug in negative x, we end up with the opposite of the original function, negative f of x. So what's implied here is that if there is a point on the graph xy, then there is another point on the graph negative x comma negative y, and we can see this here in a pretty common odd function, y equals x cubed. Here's the graph in blue. There is some point on the graph x comma y, and 180 degrees around the origin from there is another point, negative x, negative y. Those are even and odd functions.